Okay, so in the previous video, I showed you how to implement regression analysis on Excel. So based on the results, I'm going to explain three different things. First, I will apply the statistical methods we used to estimation problem of beta 1, the slope. Particularly in this example, suppose that we are interested more on marginal cost. Fixed cost can be done in a similar way, but in many cases, the coefficient beta 1 is of bigger interest. So we are going to use confidence interval hypothesis testing. We already have seen them. Okay, and the second thing we can do is prediction, right? Especially like say next month, I'd like to produce 10 units. What would be the cost? Something like that. So that is possible. And finally, we are going to use residuals. Our residual is the amount that we could not predict. Or you can interpret that as a kind of error, right? We cannot predict errors. So in the estimation, we call that residual. That is unexplained part. So using that, we will check the accuracy. What is the best way to minimize the residuals, right? Okay, let me start with the first part. In this video, I will only do the first part. Okay. First, now think about what we learned in chapter 8. Point estimator, the first column. Let me go back here. So we are talking about this guy. So this guy is the point estimator for the marginal cost, which is 2.38. And then in chapter 8, what we learned is when you check if a point estimator is good or not, there are two criteria. One is unbiasedness, and second one is efficiency. Unbiasedness was related to the expected value of the estimator, and the efficiency is related to the standard error or the variance of the estimator. So that is more theoretical part, and I'll just give you the results. It is known that mathematically you can show that the OLS estimators are unbiased. Of course, it is built in Excel. That means the estimators are good enough, right? So unbiased. Also, in terms of efficiency, mathematically you can show that they are most efficient estimators among some regular estimators, right? Without any cheating, right? Among statistically regular estimators, they are good. They are smallest, okay? And that explains what this guy is. It's a point estimator. Excuse me. It's a point estimator. That is good. So mathematically good. Okay, we studied this part. And second, standard error of the regression. So now think about the error term, right? So this is basically the noise that we need to handle. If this is small, then our estimator will be more accurate, right? All the errors are coming from epsilon here, right? So this error should be estimated. We would like to estimate this error. We call that the standard error of the regression. In this regression, the accuracy, the noise, is determined by this guy, epsilon. So its standard deviation is estimated. It can be estimated this way. So epsilon is replaced by estimated epsilon hat, right? Because epsilon itself is unknown, but you need to estimate that. And what is interesting here is denominator is n-2. Denominator is n-2. That's because we have two parameters. So also now recall what we learned in chapter 8. So when you estimate the variance, the denominator should be n-1. Denominator should be n-1 to make it unbiased estimator. the reason is, the intuition for that is because we are like, you have n number of observations, so the amount of information is n, but one of the information is used to estimate the average. So when you calculate the variance, beforehand you need to calculate the mean. So in calculating the mean, you already have consumed one of the information, right? And then after calculating the mean, the only then the remaining information is n-1, and using that n-1 to calculate the variance. That was the intuition. Here, when you calculate the standard error of epsilon, before doing that, you need to estimate two parameters, beta 0 and beta 1. So, out of n observations, you have consumed two of them in beta 0 and beta 1. So, you have to deduct that much information when you calculate the standard error of epsilon, standard deviation of epsilon, right? So when you calculate the standard deviation of epsilon, the available information is only n-2 because you have consumed two units of information. This intuition is general. Like when you have more parameters calculated before calculating the standard deviation, then the denominator will be smaller. You need to subtract more number if you need to estimate more parameters. Okay. So this standard error is given in here. So this is the standard error of the regression, the standard deviation of this epsilon, right? So we learned this guy. Of course, number of observations, that is obvious. And that is important. The standard deviation of epsilon should be calculated first because we need that to calculate the standard deviation of the estimator, right? As I said, the standard deviation of epsilon, standard deviation of the error term, determines the accuracy of your estimator, right? So accuracy of the estimator can be calculated this way. The accuracy of estimator is proportional to the standard error of the regression and inversely proportional to square root of n-1, right? So also we are using -1 because beta 1, before beta 1 we have beta 0. Anyhow, so form is similar. Like this part is comparable to the standard deviation of x bar. Standard deviation of x bar is standard deviation of a single variable divided by square root of n. Similar structure, right? But what is different? The difference is another difference is that you have to standardize, divide this guy by standard deviation of x. That is because our linear regression model, in our model, beta 1 is multiplied to x, right? So standard deviation of beta 1 and x are kind of entangled to each other. So you need to divide the other part, right? In other words, what I like when you have like variable x, so when you try to estimate something, you'd like to vary x. That is the basic idea of experiment. When you vary x, you'd like to see how much y changes. That is experiment. So variation in x actually helps estimating beta 1. So if x varies more, variation in x, standard deviation in x, the greater the standard deviation in x, then the smaller the standard deviation of beta 1, which means estimation is more accurate. So better estimation when you can have more power to vary x. So there are different ways to understand, interpret the formula. Anyhow, this is calculated. Calculation is done by Excel. So this guy is calculated according to that formula. And of course, for beta 0, the formulas are similar, so I will I will mark them done. Also, I will mark this green. So we cleared these guys. And standard errors are calculated. Okay, then the next step is confidence interval, the second part of chapter 8. So to understand the confidence interval, we need to think about the sampling distribution. And as usual, we are going to invoke central limit theorem. Central limit theorem guarantees that the sampling distribution of the estimator is approximately normal distribution with the mean of the normal distribution is the true parameter, which is unknown, but the standard deviation part is already estimated, right? We can use this guy, the calculated standard error, for the approximation standard error. Okay, so given the sample size is large, by the way, our example, the sample size is only 12, so the approximation could be quite wrong. But anyhow, so if you had enough sample size, then you can approximate it this way. Then based on the normal approximation, we obtained confidence interval like this, right? The point estimator plus minus top alpha over 2 value from the standard normal distribution times standard error of the estimator, right? So you know the point estimator, you know the standard error, and you can calculate z alpha over 2 from the standard normal distribution table, right? Standard normal distribution CDF. So you have everything. It is almost identical to the formula we had because both are based on the normal approximation, right? So x bar plus minus something times standard error. So this guy is also standard deviation of the point estimator. So basically same structure because both are approximated to normal distribution. And these confidence intervals are calculated here. So because 95% is the standard, it automatically assumes 95%. So you may change that in the option. So in regression here, you may set the confidence interval, confidence level, like different from 95% here. You may choose that. But here we already have confidence intervals calculated by Excel. Okay, so we cleared these two guys. Then hypothesis testing, we are moving to chapter 9. So the starting point, the starting belief, null hypothesis is that the marginal cost is 0. If you believe that the marginal cost is 0, then T statistic is beta 1 had the point estimated beta 1 minus your belief. But minus belief is 0, so that part is gone, and standardized by the standard error, right? So compare the T statistic to the formula we learned in chapter 9. Same. So point estimator of the population mean and your belief about the population mean and standardized by standard error. So basically the same structure. I just did not. So this minus mu0 part is 0. So that disappears. But basically same formula. And then given the T statistic, how you calculate the p-value is also the same. Because calculating the p-value is based on the normal distribution assumption, approximation. So based on the same approximation, you have this p-value. Okay, so you get p-value and t-statistic here. You have those numbers, right? So now all these things, these guys in the third table are already learned. You know them, right? You already know how to understand them in earlier chapters. So that's how I designed this course. Okay. So then it is, but what Excel does not do for you is making the final decision. So suppose that your belief is beta 1 equals to 0, marginal cost is 0, and against two-sided test, two-tailed test, and the significance level was 1%. Can you reject the null or not? It is still your decision, right? The answer is yes. P-value is 0, which is lower than the significance level. Then you have to reject the null hypothesis. So you have to reject. The answer is yes. Okay, so that means your hypothesis means that X has no effect on Y. So, like when beta 1 is 0, increase in X does not change Y. So that means X does not explain Y at all. Y is not determined by X, right? So in some sense, this means that your regression model is useless. X does not work at all. So this is an important hypothesis. So you wanted to reject it. If you could not reject it, that means your regression model is meaningless, right? But because you rejected it, actually it is a good news. It is a good news, and we call this the coefficient is statistically significant at the significance level alpha, right? By the way, in the history, if you look at the history of linear regression is longer than the history of statistical hypothesis test. So statistically significant, this term is coined in the context of linear regression first. And then later, the hypothesis testing theory is formulated to justify how it works. Okay? So that's why the terms are not clean. Like different terms are used in different contexts, and very non-intuitive terminologies are used in many places in statistics. Anyhow, so we wanted to reject the null hypothesis, and we wanted to have a small p-value. So that is good news. Okay. So in the next video, I will use real data, and I will go through the same things again. Okay. Thank you for watching, and we will see you in the next video.